We stand on what feels like bedrock. The protons and neutrons anchoring your atoms have survived for billions of years, implying an absolute, unshakable permanence. But in the deep architecture of quantum field theory, permanence is often a lie. The universe is governed by a ruthless thermodynamics. Everything craves the lowest possible energy state. Water rushes down mountains, hot coffee cools to match the room, and electrons dive to the lowest orbits they can find. We assume that ordinary matter, the stuff of stars, planets, and your own DNA, has reached the bottom of this energy valley. We assume we are safe. But the equations of quantum chromodynamics whisper a terrifying caveat. We might not be on the floor. We might be stuck on a ledge. To understand this precipice, we must look inside the proton.
It is not a solid sphere, but a frantic, boiling sea of gluons binding together three fundamental quarks, two up and one down. This triad is the stable building block of our known reality. However, nature provides a menu of 6 quark flavors. The others, charm, top, bottom, and strange, are usually too heavy and unstable to persist in our low-energy world. They decay instantly. But physics is a game of context. If you change the environment, you change the rules. Back in the 1970s, physicists realized that under extreme density, the rules of stability might flip. Consider the Pauli exclusion principle, which forbids identical particles from occupying the same energy state. In a dense soup of just up and down quarks, the energy levels fill up quickly, forcing new particles into high energy states. It is a crowded room. But if you introduce a third type, the strange quark, you open up a whole new set of seats in the room. Suddenly, the tension drops.
A triplet of one up, one down, and one strange quark, known as strange matter, could theoretically pack tighter and sit at a lower energy level than any combination of just up and down. This is the anomaly. If this strange matter hypothesis holds true, it means the entire periodic table, every element from hydrogen to uranium, is not the finished product of the universe. We are merely a high-energy glitch, a temporary arrangement waiting to collapse. We are metastable. Think of it like a lake high in the mountains. For eons, the water sits calmly, held back by a dam of rock. To the fish in that lake, the water level is a fundamental constant of the universe. But the valley floor is actually thousands of feet lower. All it takes is a crack in the dam, a nucleation event, for gravity to assert its rights and drain the lake to the true bottom. In our case, the lake is the sum of all baryonic matter in the cosmos. The true bottom is strange matter. We are surviving only because there is a significant energy barrier preventing our protons from spontaneously dissolving into this more efficient form. The probability of your atoms randomly tunneling into strange matter is vanishingly small. But the danger isn't spontaneous combustion. The danger is infection. Because if you introduce a piece of the true bottom to the lake, if a droplet of strange matter touches ordinary matter, it invalidates the barrier. It opens the drain.
From that potential energy precipice, we descend into the mechanics of the catastrophe itself. If strange matter is the preferred state of the universe, why hasn't everything converted already? The answer lies in the activation energy. The universe has built-in safeguards that prevent strange matter from forming in the vacuum of open space. The energy required to forge the first strangelet, a subatomic nugget of this material, is astronomical. It demands pressures found only in the crushed hearts of neutron stars. In these stellar corpses, gravity is so violent that atoms dissolve. Protons and neutrons are mashed together until they lose their individual identities, becoming a continuous fluid of quarks. It is here, in the dark, crushing silence of a neutron core, that the transition likely happens. The pressure overcomes the barrier, and ordinary quark matter collapses into the lower energy strange state.
The entire star might quietly convert from the inside out, becoming a strange star, a dense, city-sized sphere of pure, stable zombie matter. If these objects stayed isolated, we would be safe.
But neutron stars do not always die alone. They dance in binary pairs, spiraling inward over eons until they collide. When they do, they unleash kilonova explosions, shattering their crusts and spraying material into the void. This is where the nightmare scenario begins. If a strange star shatters, it ejects billions of microscopic strangelets into the galaxy. These fragments behave like cosmic mines. They are heavy, invisible, and effectively immortal. And unlike normal radiation, they do not simply pass through you. They hunger for stability. This is the mechanism of the contact conversion. Imagine a strangelet drifting through space and striking a planet. It is not just a kinetic impact. A strangelet is likely negatively charged, while atomic nuclei are positive.
This electrical attraction drags the nucleus into the strangelet's surface. The moment they touch, the extreme stability of the strange matter acts like a gravitational singularity for the strong nuclear force. It eats the protons and neutrons, disassembling their up and down quarks and instantly reconfiguring them into the up-down strange pattern. This process releases a massive flash of binding energy, heat, and creates a larger lump of strange matter. This larger lump now has a bigger surface area, allowing it to touch more atoms. The reaction becomes exponential. It is not a fire that burns fuel. It is a phase transition that rewrites the laws of physics for whatever it touches. Recent theoretical work in 2024 has attempted to map the density of these potential wanderers. If strangelets are stable, they would act suspiciously like dark matter, massive, non-luminous, and interacting almost exclusively through gravity. This offers a chilling solution to the dark matter mystery.
The invisible halos holding our galaxies together might be composed of trillions of dormant strangelets, nucleides, drifting in the cold. We could be moving through a diffuse cloud of universal solvents, surviving simply because space is vast and direct collisions are rare. But the statistical probability is never zero. A single microscopic impactor would start a conversion event that consumes the Earth, transforming a vibrant biosphere into a hot, sterile sphere of strange matter in roughly 1 hour.